Well, I'd like to thank the organizers for inviting me to give this talk. I was thinking that this might be a slightly more general audience and not everybody would know about the details of geometric algebra. What we're going to talk about here is some work that I'd like to say I did with Stefan de Koning, but really he was the one doing most of the work. It's explaining the basic work of other people for the classical mechanics in a way that we found productive to think about geometric algebra. So the results are not necessarily ours, but the format of the talk is. When you go to geometric algebra, and now I have the same problem as the previous speaker, that it doesn't go to the next slide, but now it has. So if geometric algebra is so great, what can I do for classical mechanics? That's the thing I'd like to treat now. And what we will demonstrate is a coordinate-free geometrical representation, which unifies the linear and the angular aspects, you know, the angular momentum and the linear momentum, for both the objects and the motions. So it's not a specialized motion representation, it's actually built, integrated with objects. It can be integrated numerically rather easily, as you saw from the little blob that I had there. And it also naturally upgrades existing vector methods. So what you have done, you can incorporate in there, but you'll see that you'll get additional values from that. It has historical provenance, screw theory, spatial vectors, and Stefan learned it from Charles Gunn. But I think it's more easy to develop it from scratch in half an hour. So that's what I'm going to try and do. And what you saw in this little demo, let's make sure that it works again, is that, yeah, we have real-time computation of the mechanics of a block on a string to look forward to at the end of the presentation. I will be talking first about kinematic geometry. So how do we represent Euclidean motions? And we use a special algebra for that. And then in the second half of the talk, I will go to including the dynamic physics and going to the Newton-Euler equations and how that sheds a light on how we used to do things and how we should do things. The general principle of any geometric algebra in our mind is that the operators are central. You're developing a geometry, and that geometry for geometric algebra is established by going to orthogonal transformations. Now, classically, you wouldn't like to do that because orthogonal transformations are very awkwardly constrained matrices. But in geometric algebra, we have a very natural representation for orthogonal transformations. And so whenever we can put our symmetries in that form, we're very happy because we get a nicely equivariant way of transforming anything in the space in the same way. And that is based on the Cartan-Dieudonné theorem that you won't need more than n reflections to make an orthogonal transformation in an n-dimensional space. And that's going to be our guidance in the whole setup. Well, what do we want to do? We want to do Euclidean motions in our regular 3D space. And if we impose this view of seeing them as multiple reflections, then we would say that there are two types of basic motions. One of them is a translation, and that's a reflection in two parallel planes. And the other one is a general rotation, which is a reflection into intersecting planes. And if I take such an object X and I reflect it, I obviously translate it. But if the object had been a line and I have a way of reflecting a line twice, then I also get a translated line. So this means that in order to do Euclidean geometry, we should go and find an algebra in which the planes are represented as the vectors, because the vectors are going to be the reflectors. And then our Euclidean motions will become even orthogonal transformations. We are going to represent them as rotors. I will give the details, but we'll find that they can all be written as the exponential of a bivector, and the bivector turns out to be the really handy hook to characterize any of the motions. Now, classically, if you tell people that you're going to build motions as multiple reflections, then they will have this formula in mind, that you will have a vector x, you will have a plane with a normal vector A. And in classic linear algebra, you have to do something like this to reflect the vector X and obtain the reflected thing. This is, of course, not something that looks fundamental and looks very useful for motion representation. But if you've known a little bit about geometric algebra, you know that this dot product that we use so much in linear algebra, in geometric algebra is seen as just the symmetric part of a deeper symmetry, the geometric product. So if I replace this by the symmetric part of the deeper product, and I want to do some simplifications which assume reasonable things like associativity and distributivity, then I find that I can simplify this complicated formula for this simple concept of reflection into something that is a sandwiching operator. I take the object that I want to reflect in, and I sandwich it. I sandwich the object that I want to reflect between the two, the object I want to reflect in. There's a minus sign, there's an inverse, but the inverse turned out to be very simple to implement. And the minus sign you have to keep track of because there's a difference between even transformations and odd transformations, as we also know from linear algebra. The nice thing about this sandwiching representation as opposed to this one is that it's obvious that if I do the sandwiching operation again with another plane B, then these things group together into elements that should again be part of the algebra because they're a geometric product. I just simply have a geometric product as the composition of my reflection operators. And moreover, we can also expand the element that we operate on. I'll give some more details of that. And then we get a more general formula that allows a general composition of reflectors, in our case it will be multiple planes, to act on a general composition of operators, for instance, the intersection of planes such as lines. And this reflection and sandwiching is the core of the geometric algebra representation. Okay, back to 3D Euclidean geometry. What we then want, if we want to do multiple reflections in planes, is to find a representational space in which a plane is represented as a vector, because geometric algebra in its abstract way acts on multiple vector multiplications. Well, I think probably everybody here knows how to do it. You use homogeneous coordinates, right? You have to specify the normal vector of the hyperplane, and you have to specify the distance from the origin, and then you get a n+1 dimensional vector that represents a general plane. It's the same thing in geometric algebra. That is exactly the representation that you borrow, but it turns out that there is something special that you don't usually do when you have homogeneous coordinates. You have to specify the metric of the space that you're in. You have to say what it is to take the dot product of two planes. It has to be reasonable, and the only way to get it reasonable is to make your representational space not returning your outcome. And you do that by making this a very special dimension in which E0 dot E0 equals 0, which is why we denote it with a naught. At that moment, we are in the algebra of planes. And for a d-dimensional space, that is Rd, 0, 1, this says it's just Euclidean dimensions, and this one says there is an extra dimension in which things square to 0. Does it work? Well, if it should work, then we should have that if I have P1 and P2, so a reflection in this first plane and then a reflection in the second plane, together should form an operator that acts like a translation. And indeed, if we use the rules that we have before, we get something of a special form, which we can, because of the special property that E0 squared equals 0, can write in an exponential form in which we see something like the translation vector occur. And this is indeed the operator that if I apply this multiple ways, then I'm actually implementing the translation as an even number of reflections in parallel planes. And this works. If I do a rotation, I would do it by a reflection in intersecting planes. There's a little bit of math which I hid because you get some expressions that at first sight you don't quite recognize, but it turns out that it actually indicates this line here, this intersection line, as the thing that the rotation occurs around. So as opposed to linear algebra, where you have to do your rotations around the origin, otherwise they're not really proper rotations. You know that in homogeneous coordinates, you get rotations that are offset, but we even get them as orthogonal transformations here. So an element appears automatically in the algebra, which is that line, the intersection line of the two planes. And it turns out that that line element is something that squares to -1. So that allows you again to pull this together into an exponential form. Now, basically, this is the basis of dual quaternions. But if you read anything about dual quaternions, you will often find that they're based on some kind of complex numbers in a 4-dimensional space. I've not used a complex number at all here, right? I've just intersected real planes, multiplied real planes, generalized the dot product. I get things that square to -1, but this is just a consequence of the math, not of going to some abstract representation, which I no longer understand. And when you look in the detailed code of people that use unit dual quaternions, you see that they don't understand them. Something interesting happened though. We started with the operators, and you saw that this line, this intersection line between the planes played an important role. That is something where you can say that you can express any of these motion things, we call them motors, as the exponential of some kind of a rate, the speed with which it moves, times some bivector that is kept invariant. Where does that come from? Well, if I take two of these planes, P1, P2, and P2, P1, so one of them is reflect first in this and then in that, and the other one is the other way around, then you can easily show that these two things are invariant under the sandwiching product. And that means you can form combination invariants. Well, we've seen that if we add those two, we get the dot product. So that's like the cosine between of the angle between the two planes, if I talk about a rotation. And I can also take the antisymmetric product, and that produces the line. That's the other thing that's invariant. So the objects that I get, the planes, the lines, the points, etc., occur again from the operation of using the operators as central as the invariance of the operator. So there's a natural integration between objects and operators. It's just that it's just the other way around than you usually do. Usually you start with the objects and then you find the operators. We find it more easy to explain it in this way. Well, we've seen two elementary motions, the rotation around a line and the translation along a vector. Of course, if you combine those in general, and you do that in n dimensions a lot of times, then you will get something that is more general. Now it is no longer one of those simple bivectors that I have here in the exponent, but I get a general bivector, but I can always decompose that into something that is a rotation around a line combined with a translation along a line, and that's the classical Charles theorem. But anyway, the motions that we're interested in the representational space that we have constructed to represent the symmetries, in our case, Euclidean motions, automatically lead to something of exponential of a bivector being an important way of organizing our motions. So keep a slight look on the time, okay. Now I've said that automatically from this concept of invariance, you get new kinds of operators. This wedge product is actually the intersection operator between two planes. And I have started with planes. I have been able to make lines. This space actually also has points, but really only as the intersection of three planes. And when you execute that with this outer product operator, you find basically exactly what you would call the homogeneous coordinates of a point, except the basis is a little bit strange because it's now a trivector basis. But everything is completely consistent. I have not done anything extraneous. I have only modeled hyperplanes as my vectors, and the rest follows from the structure. There's a dual operation. If you have 2 points, you would also like to make the line through 2 points. That's a join. I won't go into that, but it's dually related to this wedge operator. Dual means orthogonal complement. And for the following, I only need one special instance of the join, that if I have a line that moves in direction u through a point P, then it becomes this object of the algebra, U dot P. It's a small extension of the dot product to the more general things. One of the things to notice about the simplicity of programming in this is that as long as I make my composite objects out of sums of geometric products, it will be so that if I apply a motor to that composite object, it will be the same as if I had applied the motor to the individual constituents and then made the composition. So that means that anything that I make, as long as I make it as a linear combination of geometric products, will automatically transform in exactly the same way. So I don't need special methods to say a line transforms, translates like this, a point translates like this. It's all universal, and that makes your program extremely simple. And it also means that you can write a general program and later decide whether you're going to use it on a point, on a plane, on a line, or on another motor. This saves a lot of code at the highest level. And you can always make sure that the compiler executes the same coordinate-based code at the lowest level if you're interested in efficiency. Now, this is one of our geometric products. We have a merge site where we sell things. This is a very popular item. It's this complete schema now for the projective geometric algebra. So here you see that in 3D, we have different elements. We have the vectors which represent planes. We can make points as trivectors, and we can combine these things to lines. We can add these lines to screws. You saw the exponential of a general motor. But there are certain combinations that form a rotator operator. Around the origin is the unit quaternion, a translator operator, or generally the dual quaternions. The Lie algebra is in the screws. The Lie group is in the motors. Plucker coordinates are automatically present. All of this follows from following the same basic principles. And it's one framework in which these special interpretations that were invented for motions, lines, etc., find their home and their mutual relationships. If I want an operation that makes this line into this line, I just divide the two lines, take the square root, and then I have the motor that does that. So it's all integrated, it's all very nice, and it's a nice setup for doing the classical mechanics. So let's do that. Let's now go into the dynamics thing. What we're interested in is applying a force, but the force is localized. The force passes through a point Q. Well, we've seen that in the geometric algebra, it's represented as something of the form F dot Q. It's a join line moving in the direction F, passing through the point Q. And something unusual happens in the homogeneous representation. Classical homogeneous coordinates have this as well. I just hadn't realized it. If you have this algebraic object that represents this force through this line in space, and you say, well, let me see what it looks like from another point, then you find that this algebraic object remains exactly the same, but your split into a bit that is force and a bit that is not force, that's actually torque, automatically generates the right terms. This is the torque, this is the force. In the classical representation, in which you were not too specific about specifying where things happen, you had to remember to add this term to actually make your physics correct. Here we have an invariant object, the force along this line, which depending on where you stand is felt as just a force and a torque, etc. So this identical algebraic object F is represented to different terms when the focus changes. That's a very, very nice property, because that means that you can set up your equations in a geometrical way and later decide where you're going to use them. There's a little bit of dark magic that I didn't find the time to explain in detail, but if you have an object that moves under a motor, so a time-dependent motion of an object x0 to become the x that it is at the moment, then it turns out that the derivative of x, so how much does x change, is the commutator with the bivector of this motor. And the bivector of this motor, when it's time changing, is basically the relative derivative, the derivative of the motor divided by the motor itself. These are somewhat straightforward computations, but not in a half-hour talk. And This motor rate B is like a screw. It combines the linear and the angular velocities in one bivector. That's going to be very advantageous. And the reason we can do that is, again, this is the linear part, this is the angular part, but in the geometric algebra representation, the two are united in one invariant element. So we're going to specify our motion equations in terms of these invariant elements. And then, yeah, if you want to split them in linear and angular, that's your choice, but you don't have to. So now I'm going to take a heavy mass point with at a certain location. And I am going to see what the angular momentum is if this point moves. Well, it moves from the location where it is to the location a second further. So the derivative is added. I expand this thing. I know that the x dot is something like the commutator product with the bivector. And so I get something that is a linear function of the bivector. And this is, in similar circumstances, you would call this the inertia tensor. But this is now an inertia that contains both the linear and the angular momentum. It is a linear map. It's also dualization, but I won't go into that. And if you split it out, if you say again, okay, this is this nice geometric object, but I want to know what it is relative to the centroid of the object that I'm moving, then you find that it automatically, this object remains algebraically and computationally the same, but I then get a split into something that says, well, it's this much linear momentum around along the centroid, plus a bit of angular momentum related to the inertia of the object relative to the centroid. But in the geometric algebra representation, if I have one object and I glue it to another object, I can just add those inertia maps. I don't have to say, oh, wait a minute, there's the Steiner's theorem that if I have the inertia here, I have the inertia there, I have to transfer by the parallel transport. No, the variability of the inertia map is allowed to say, I don't know which axis I'm going to rotate this object around yet, but my map is powerful enough that I put the axis in, I get the correct inertia. And that's different from the usual formulation. Well, now we're done. Because we have this integrated force and torque, which we have called the fork, so that we could say, may the fork be with you in our write-up about all of this. That equals the change of momentum. Well, the fork now contains both parts. The P also contains both parts in the B. You see what it is to take the time derivative of the P, and it is something like, well, okay, time derivatives was the commutator with the B, but there's also the part that B itself may be time varying, and you get two equations. And the implementation that we make is directly of these equations. And that's, I'd like to go to that now. Let me see. Okay, I think it's better done from the next page. So we get a split in two things. You know, the force that I have through the shape of the object, which is encoded in the I, somehow determines the rate bivector by solving this equation. And then that rate bivector can be used to say, okay, but then the motor, the actual motion, is by this equation. There are two coupled equations. It may be, it looks in its formulation very simple. The implementation is also very simple. I just have a state description that contains my motor and my bivector. I know what the update equation is for my motor. I just showed the equation. I know what the update equation is for the bivector. The jewel here represents that inertia map. And now I have to specify the forces, and let me show that for this one. So the forces, I'm going to do a block moving in gravity. So I have the gravity pointing downwards, which in this case is the E2 direction. It's represented by E02, that is the intersection of the plane at infinity with the direction 2. It's a vertical direction, but I need, because it's a force, I need a join line, so there's a dualization. And also because I need the force in the body frame, I have to imply the inverse of the motor to actually get it from the, I didn't say that explicitly, to get it from the world frame to the body frame. And we compute in the body frame because it's easier. The Hooke-Spring law is there's an attachment point in the world. I have to transform that to the body frame. I do the join operator with one of the points of my object. That already is a join line. Let me just run the demo and we'll see it better, I think. Okay, that was the wrong demo. It's this one I want. So here we see this thing implemented. And if I now drag the object, you can see that I can move this along. I'll zoom it out a bit. And it integrates it in real time. And over here you see this code defines the cube. This code defines the forces. This is the derivative of the state operator, those two equations that I have. And this is a simple Euler integrator, not even an RK4 integrator to perform the computation. But you may be disappointed that this is in 2D because I was saying that I was treating this in 3D. So let's change the dimensionality. The code is exactly the same. Save and run. The code is exactly the same. And the reason is that I have specified everything in terms of hyperplanes. I have specified that there is a force in the E2 direction. I haven't said how many other dimensions there are in the space that I'm dealing with. It could be 3, it could be just the 2 dimensions. The specification by the normal vector is independent of the dimensions that come later that have to fill that space. And so exactly the same code works in 1 dimension, in 2 dimensions, and let's make it 4-dimensional. This is the dynamics of a tesseract on a string. There is no change in the code, absolutely not, because specification by saying, I know what happens in these spaces and the rest you fill in because nothing is happening there, is automatically done. And so one of the things that we're using this now for is we have a student who is trying to learn 3D dynamics of situations by first looking at the 2D situation, learning that in a network, and then popping up the 3rd dimension and using what it's learned in the 2nd dimension to expand it to the 3rd. And we hope that's going to be successful. Keep my eye on the time because my chairman is gone. I have all the time in the world. So the integration then is that in algebraically, we have hyperplanes that together meet in one of those axis lines that I can rotate around. That determines the rate, and that's the kinematics part of the picture. If I look at the dynamics part of, I'm interested in momentum and force, and those are the join lines that are formed by connecting points. In any dimension, the connection of 2 points gives something like an orbit. In any dimension, the intersection of 2 hyperplanes gives something like the axis. The 2 are dual, and the conversion of one to the other is actually done by the object properties that are here in the inertia. So I hope, it's very brief, but I hope you are somewhat convinced that this might work and that with so little information you can do it. So now let's destroy it and let's go back to classical mechanics. What do we have to, so this is in our mind a nice symmetrical picture of look at bivectors and you have everything. Well, what are we going to do to get to the classical formulation of how we are taught classical mechanics in school? Well, we don't use homogeneous coordinates. Physicists don't use homogeneous coordinates. That means that you have now integrated translations and rotations. So that means you have to treat linear and angular separately. Then you're going to say, well, I don't know geometric algebra, so I'm not going to use bivectors. Now you have the problem that you have two things that act differently, namely the linear translation and a rotation axis that you both want to represent by vectors. So you have to introduce polar and axial vectors. Then you're going to say, yeah, I know where it happens, but I'm not going to put that in my formulas. I'm going to put that in the text. I'm going to say in the text that imagine that you stand at the centroid and what happens there. And then if you move somewhere else, then I have to import other things like the parallel transport theorem of Steiner to make my equations correct again, because they're not automatically correct, because I've hidden essential information, not in the formulas, but in the text. And then you tell your student that's how nature is, and you persist for 350 years. I decided that was a bit too strong. In screw theory, we could have known this after screw theory, which is 150 years ago. That's a negative way of looking at it. The positive way is that this is actually rather fully integrated, and you can upgrade your classical vector mechanics to this invariant formulation in PGA very easily. If you have something like, let's say, the momentum, then you classically save the P and the L, the linear momentum and the angular momentum. And in order to make this invariant bivector now that handles so nicely and that is universally integratable, you just have to form the bivector element out of those two components by saying, I know where the linear momentum was P, and that is at the centroid. And I add the angular momentum as, well, this is, if you want to make it geometrical, it's in the plane at infinity, but that sounds very strange, but it's the ideal part, accompanied by this null vector. This is the E0 that I bet. Now you have made something that you can directly put in these equations, and now you can use the nice properties of these equations to integrate them in the way that I showed you. Same thing with the forces. If you know that the force runs through a point R, but has a torque as well, then you make this element, and now it doesn't matter anymore how you made it. In any base that you re-represent it, it takes automatically the correct symmetry, parallel transform, etc. So it's not hard to upgrade to the GA. This is what you have to do. And this is here, rotation and translation are opposite, because this is one of those dual bivectors. So it does really clean things up. We do have options, objects and motions in an integrated framework. In fact, we just started with the motions and we made the objects that transform nicely in that. Bivectors are crucial to this representation, because that's how things change with the commutator with the bivector. That's the Lie algebra if you want to open another math book, but why would you? I mean, just get a GA math book and it contains it all. It unifies Newton and Euler, let's say the linear equations and the angular equations. The inertia is additive, which is addictive. A very simple and efficient code results. You can easily integrate these things because you have both elements available. And what I wanted to show specifically is that you don't have to forget the old things. You can just upgrade your old things into this new way of doing it by this simple equation. And I do want to say for completeness that this is a lot of the aspects that are here in a unified framework. The unified framework is a bit nicer than it used to be, but the elements that have been discovered here are also part of screw theory, spatial vectors. And they remain valid in ND and even in our other metrics as well. This shirt is also available. All the cool vectors are by, because it's one of our commercial things. Now, this is a fairly new way of looking at it. We've written a bunch of tutorials. We've had some video tutorials. Whenever you want to know more, bivector.net is a good source to get the latest connections to software or demos. And whenever we have presentations or videos that we think are useful, we put them on there as well. And that concludes the presentation. More or less on time.
Thank you very much. My first question is, do you have this cap here with you?
No. I decided not to do it. My wife said it's not about you.
Okay.
I don't know why not, but.
Okay, so we have time for questions.
Yeah, thank you. 2 questions. I caught you saying projective geometric algebra. I thought you and Stephen had decided it was called plane-based geometric algebra.
Did I say that?
You did.
Oh, I'm very sorry. Yes.
So
it's my accent. Yeah, that's.
So
no, so it's actually almost deserves to be called Euclidean geometric algebra, in the same sense that conformal geometric algebra gives you versors that do conformal transformations, and here the versors give you the Euclidean transformations. But it was too late to change. It was already called projective geometric algebra by Charles Gunn, although he has different varieties because he also looks at the different metrics. So he calls it Euclidean projective geometric algebra. The projective nature is more the reference to the homogeneous coordinate usage, which is also present in other models. So we didn't think that that was very indicative. But yeah, since I have the P, since I was stuck with the P, I usually try to say plane-based. Yes, thank you.
Okay, so second question. So Anthony, Chris, Robert did a lot of the classical mechanics back in 2010 in CGA.
Yeah.
And actually used, tried to implement, Geomerics implemented some of the stuff. Then Hugo did a lot of, the screw theory. Put it in this way in CGA, and we could project down to this. But, he also found it very easy to implement constraints. So things which were constrained. So can you do that in, because a 4-dimensional algebra is better than a 5-dimensional algebra. I still don't like the nullness, the null vector.
No, that's continuing work. So Chris wrote a nice thing, which we refer to in bivector.net as well, about the relationship between the CGA and the PGA, and how is one a subset of the other. And you're totally right that since it so naturally grows into the next one, when you have a particular type of constraints like Hugo did with the spherical constraints, it's very natural that you want spheres as basic elements of computation. And so then you automatically become a member of this higher algebra in which these constraints are more easily represented. So what I didn't do here was contact or constraints. For all these techniques, we have some hints and also pointers to that the paper by Hugo, where this is just the raw basics, the minimum. But for practical dynamical systems, you do want to look at the context, you do want to look at the constraints, and then the natural membership of this to the other ones that extend it, in which it sits very easily, is very convenient because it automatically becomes upgradable also as your program. Okay. Yeah, thanks for that. I had wanted to say that.
Any other questions? Okay, we have here.
Hello, so very nice presentation. So I'm trying to understand the PGA, and maybe I have a basic or a stupid question. Is it possible to, using PGA, is it possible to represent translations in an orthogonal way?
Yep, because of this special metric.
So this means that it's not necessary anymore to use conformal geometric algebra. We can use just PGA.
No, and I would recommend reading what Chris wrote if you've done the conformal geometric algebra. So what put us on the wrong foot is that we were always thinking about points as the basic constructors or spheres as the basic constructors. And then in the conformal geometric algebra, you need both the no and the ni, the n0 and the n infinity to make this point. And then when you want to move them around, it looks like you have to drag the whole algebra around. If you go to planes, you see that one of the basic vectors disappears. You only look at the ni, the infinity part. And if you now pay the small price of constructing your point as intersection of planes, a subset of the algebra is enough to generate all the motions. You just take you cut out a certain part, you never use no. Never in the conformal geometric algebra. But you do that by taking the slightly dual point of view that hyperplanes are the ones that are important. And that is consistent with Cartan-Dieudonné that multiple reflections generate the Euclidean transformations. But whenever we want to do something slightly more advanced, like Joan was pointing out, we find ourselves naturally popping back up to CGA. Anthony is burning to say that he has another way of reaching the same kind of structure by the one-up approach, where he comes from the non-Euclidean geometries where you don't have that awkward zero element, and can still make the Euclidean geometry also by taking one more dimension than the Euclidean dimensions. I have lied for many years in saying that the conformal model was the smallest possible way of making Euclidean geometry. It's just not true. You know? Don't buy that book or cross that out. And Charles kept telling me, and he was right.
Okay, so we have a question on the chat. Hamish, can you unmute yourself?
Hamish.
No?
We talked last week. You have another question?
So let's try to, yes, just 1 second.
We have to unmute him?
Yeah. Ask to unmute. Yeah.
Ask to unmute.
Thanks a lot, folks. Yeah, sorry. So fortunately, the thing I've got a question about is on the slide that we're looking at right now. So do I understand? So a screw is a bivector to us, but a screw motion is a motor. Yes.
Mm-hmm.
Okay, that's all I want.
Difference between, you know, the Lie algebra and the Lie group.
Okay.
All right. So we have time for one more question.
I'm understanding this, I believe, from a point of view, I'm seeing objects and by reflections and planes. You're doing all the things you've described with PGA. Is it straightforward then to say that what you're looking at is staying fixed, but your point of view is moving, your camera is moving?
Well, so you have done the space-time algebra, right?
Yes.
Electromagnetic fields. You have the projective split there, that there's one bivector field, and depending on how you move through it, you feel certain components as electric and others as magnetic, right? It's that's split what you need to do, that it depends on your motion. Well, here it's not with motion, but the principle is the same. There's one unified object, and when you go to a different location, you recognize one part. The infinity part becomes the rotational part, and the other part is the linear part. It's just a split. It's a deeper concept than going to a different coordinate frame, but it has that same feeling. You separate things into components that you have given different names, but there's no algebraic reason or even geometric reason to do so. You can just keep computing with that invariant object. And that's, we knew that for electromagnetism because of David and the Cambridge group. But now it's also true for the...
I guess I was also thinking of the point of just simple cameras. If you're driving along a street and you take a picture of a building at one moment, and then you're further down the street and you take a picture of the same building with a fixed camera, well, your camera's in a different position. So,
well, you know, that's different. Then you're talking about occlusion and things like that. It's, yeah.
Right.
Okay, thanks. I cannot look through you. I have to move to do that, but yeah.
Okay, so help me thank Leo once again for the amazing talk. So right now we have a break. So in the same place that we had the drinks last night. So please, you can go there right now. Thank you.